So in this scene, I've just got a couple of bones here and a couple of muscle objects. So what I'll do first is convert this bicep mesh here to a Ziva tissue mesh. So what I'll do is select it and then come into the Ziva menu. And then under Add Simulation Component, I'll select Tissue. So the cool thing is with Ziva is that we don't force you to use any kind of muscle primitive like a NURBS tube or anything like that. So Ziva will ingest any sort of arbitrary Maya polymesh that you can come up with basically, and it'll work with that. You can make a tissue out of almost any Maya polymesh. So what that allows for is, you know, an enormous amount of freedom, I guess, with the level of fidelity that you want to make your tissues, and it also means you're not limited to just making muscles. You could make you know, couches or fat or car tires or any of that kind of stuff. So you notice when I converted that object to tissue, we got a couple of new things in the scene. I'll just minimize this. And one of those is this solver node. And this has some general kind of properties about the Ziva system. Things like collision detection and gravity. The solver scale is important as well, but we can talk about that stuff later. Of course, there's sub-steps here as well, which is important for simulation quality, but we'll leave all that stuff at default for now. And then what I'll do is just play back the scene now, and you're going to see this tissue object just drop in space because it doesn't know anything else about the system at this point. So you can see that gravity's being applied and the object is moving through space. You have to move that little window out of the way. That's cool. Can I put that there? Okay. So what we want to be able to do now is we want to be able to attach this tissue object to the bones in the scene. So what I'll do is convert these objects here to Ziva bone objects. And Ziva bone objects are kinematic objects, so that's different to the tissue objects, which are dynamic, they're simulated. Whereas the bones are kinematic, meaning that they themselves are not simulated, but they do contribute to the simulation in that you can attach tissues to them and you can collide with them. But the idea with Ziva bones is that they're driven by basically any way that you can drive a Maya mesh. Any way that you can move one in Maya is a valid way of driving a Ziva bone. So anything like if you were to key the transform, for instance, or a parent constraint, or a deformer, or an limbic, all that stuff is a valid way of driving Ziva bones. Okay. So with the object selected, I'll come under the Ziva menu, add simulation component section, and this time I'll choose bone. And you can see that it added the bone successfully because we have these white draw points on the vertices of the geometry. And we also, if you look in the channel box, we also got some extra nodes here, one of which is the Z bone node. And this has some properties, which we can talk about later. But the next thing I'll do is add these two. So you can select multiple objects at once. So with these two selected, I'll also make those Ziva bones. And if I play this back now, you're not going to see any difference because the tissue object is not yet attached to the bones. So what we need to do in order to make that happen is to make some attachments. So what I'll do is grab a couple of vertices on the bicep mesh, and then I'll shift select this radius bone. And then what I'm going to do is come under the Ziva menu and then add simulation component. This time I'm going to select attachment. And you can see in the channel box now that we've got a new node. This is a Z attachment node and has some parameters here as well, which we can talk about in a bit. And now what I'm going to do is go ahead and add the bicep at the other end. So I'll select some vertices here, and I'm going to add these ones as well. And then I'll shift select the target object, which in this case is the humerus bone. And then under the Ziva menu, I'm going to select attachment again. And I'll just hide the brachialis for now. And now when I hit play, you're going to see that the tissue object is just going to kind of droop down a bit. Okay. Cool. Now what I'm going to do is actually drive these bones. So like I was saying before, there's many ways you can drive Ziva bones. What we encourage people to do though is to cache out your animations first before driving your muscle rigs. So in this scene I have this, for instance. I'll hide this other stuff for now. And you can see that this is just an alembic cache of, I'll give it a few more frames. This is that same upper body ROM that we were looking at earlier. And so the idea is that the animator is responsible for, the animator has an interactive rig, and they're responsible for moving the bones around. And that way you have a clear delineation between the animation rig, the interactive rig, and the muscle rig. And the other cool thing about that is, as well, is that you don't need a Ziva license to run the animation rig, which is useful in production. So what I'm going to do is put that to the side for a second. I'll unhide the muscles and bones, and I'm just going to make a blend shape between the corresponding skeleton objects. So do that now. Do these guys. Now switch the blend shapes on. And now what you're going to see is the bones are going to move around in lockstep with the alembic cache, and then the muscle is going to follow as well. So I can move this back now as a point of reference. Cool, so you can see gravity's working on there, getting some nice secondary dynamics out of the box. You'll notice though that the muscle at this point is kind of a bit droopy. And that's because there's probably not enough information in this muscle system at the moment to stabilize the tissue object, if you like. So what I'll do as well is add in the brachialis. Just hide the bicep for now. And then, so with the brachialis selected, I'm going to come down to the Ziva menu and I'm going to select tissue. And then once again, I'm going to attach the brachialis to these bone objects. Ziva, add simulation component attachment. And then at this end, I'll do the same. Click G. Cool. So now brachialis is going to follow along as well. Okay, that's fine. Now I'm going to make the brachialis, I'm going to give it the ability to slide along the humerus bone. Just hide the driver bones for now. And to select the vertices to create this attachment, I'm going to use our select by proximity tool. So the first thing I'll select is the humerus bone. This will be the source of the attachment. And then I'm going to select the brachialis. And then under the Ziva tools menu, I'm going to come down to proximity tools at the very bottom. And there's this utility here called select vertices. Now I'm just going to leave the radius at default for now, and I'll hit select. Go into wireframe, you can see that the selection's good. And then I'll shift select the brachialis again, and I'll make an attachment. And this time I'm going to go into the attachment properties, and I'm going to change the mode from fixed to sliding. So there's two modes with Ziva attachments. And so whereas fixed is going to try and bring the objects back to where they were at the time of creation of this attachment, the sliding is going to simply try and preserve the distances between the two bodies when the attachment is created, but it is going to allow for tangential sliding along the surface of the target object. I'm just going to make this attachment a bit weaker. So you'll notice that if I select this new attachment now, and I look in the attributes, you'll see that we have two values which refer to stiffness. So the second value is the stiffness exponent. So what happens is these two values multiply together to give you the final effect. So at the moment, 1 times 10 to the 8 is pretty rigid for a sliding attachment. So I'm going to bring it down to 10 to the 6, which is 100 times weaker than 10 to the 8. And the reason we split it out like this is it's kind of a convenience tool, and what it means is that you don't have to manage, a whole bunch of zeros in your channel box and try and eyeball it. So you'll see this delineation, if you like, between the exponential value of an attribute a lot in Ziva. This comes up a bit. So now you're going to see, if I hide the bicep, you're going to see the brachialis follow the humerus a bit closer. So it can still slide up and down, you still get some dynamics in there, but it's going to follow the humerus a bit closer. And now I'm going to make the bicep attached to the brachialis. I'll make another sliding attachment for that. So with those two objects selected, under the Ziva tools, I'm going to do the select vertices thing again, and then hit select. And then Ziva add attachment. Oh. To select the bicep body again, and then select add attachment. Change its type to sliding, make it a bit weaker. And so now you can see that the tissues are still dynamic, but now they're following the bones a little bit more closely, which is cool. So a quick look at the chat for a second.
Yeah, the chat's looking good. We are saving all the questions on our end as they come in, and then
okay.
Tell them to you at the time of the question and answer.
Okay, is it worth stopping at the end of, say, the tissue part to jump in? Yeah, okay. All right, cool. So another thing we support in Ziva is the ability to add muscle fibers to tissue objects. So just like in the real world, where muscles are populated with fibers that do the actual work of contraction, we can model that in Ziva. So I'll just switch to default shading for a second, so you can see. So I'll select this bicep object, and then under the Ziva menu, under Add Tissue Property this time, I'm going to select Muscle Fiber. And you can see if you look in the channel box that we got this extra node here, this Z Fiber node. And it has some attributes about how strong it can contract and things like that. And we'll get to that in a minute. And so now, if I go back to the attributes on the fiber, you'll see one of them is excitation. So if I make this, if I change the timeline back to say 200 and say pick frame 30, this is keyframeable. It takes a float value between 0 and 1. So what I'm going to do is key it between 0 and 1 over these frames, and play this back now. And then as I step through the timeline, you're going to see the color of the fiber change, and you see the muscle contract. And now when it plays, now when I continue with the simulation, it's going to stay very, very rigid and contracted throughout the whole thing. So this is a really powerful feature to make sure that the muscles perform correctly through the range of movement that your rig is capable of. So now we don't really want to be keyframing that every time the elbow bends. So we have the ability to fire the muscle or excite the muscle based on a curve length. So what happens is when you make a Z fiber, the Ziva is going to try and guess at the orientation of the flow of the muscle. And usually does a pretty good job. So it's going to try and pick the most extreme points in the object. And you can see now, if I look right up here in the tendinous area, the fiber flow is getting a bit confused here. So I can actually edit this. Many things in Ziva are paintable. One of which is the endpoints of the fiber. So if I right click on tissue mesh and come down to paint, you'll see that there's a lot of things here that we can paint. So if I come down to fiber and then I select endpoints, and then if I look here, you'll see that Ziva's made one vertex 100% white, and at the other end there'll be one vertex it's 100% black. And we can change this whenever we want. So what I'm going to do is select this vertex as well, and then I'll go into paint, and I'm going to make this white. And when I make this, flood this to white, you're going to see the orientation of the fiber field change. So now it's going to contract in the right direction. So that's a cool thing. But back to the curve length, firing by curve length. Now I'm going to create the curve, just a 2-point curve that we can use to excite the muscle. So with the muscle selected, under the Ziva Tools menu, we have Create Line of Action Curve. And I'll select that, and we've got this curve here. And it's basically just putting the endpoints where the endpoint map is. I'm just going to change this slightly and pull this endpoint down to about halfway down the length of the radius. And then that's going to make it more obvious that when the muscle knows when it should be firing. Cool. And then I'm just going to attach the curve to the bones. So that's just normal minor rigging stuff. So what I'll do is deform, create cluster at that end, and then I'm just going to rivet these clusters onto the bone objects. So when you're authoring your characters, it's really helpful to have a script that does all this work for you, that looks up the closest point on the closest face on the bone, and then makes the rivet for you and does the parenting. I have a script to do that if anybody's interested. Cool. So now when I scrub, the curve's following, that's good. And now I have to connect the curve to the actual fiber. So I'll select the curve first, then the muscle object, and then under Ziva, I'll come down to muscle line of action. And so if I select the curve now and look in the channel box, you'll see it has this Z line of action node as an output. And if you look in the node editor, and I just graph the connections out for this thing. Move that away. So you see the curve flows into line of action, and then that flows into the Z fiber node. And so now when I play this back, hopefully you'll see that the fiber is going to contract when the elbow bends. And then the contraction goes away when the arm's extended. Another thing you can do, you'll notice at the moment that because it's a simulation, I can't scrub the timeline. That doesn't work. So while you're authoring, there's a useful thing that we have, which is a cache. And we generally advise that this is more of it's more of an authoring tool than a shot tool. It's a RAM cache. So while you can write out the data to disk and things, we recommend that you kind of pass alembics around instead of Ziva caches. So that's just a note on that. But I'll add one for the purpose of authoring. When I added it, you can see we've got this cache draw thing. And at the moment, there's no frames in it. So I'll just play now. You can see it's caching up the thing. So now when I scrub the timeline, you can see the color of the fiber changes and the shape of the muscle changes as well. Cool. So you could go ahead and then quickly do this for the brachialis as well. Ziva. So with it selected, under the Ziva menu, add fiber. And then I'm going to use the same curve to drive the excitation. So Ziva, add tissue property, muscle line of action. I'll just clear that cache. And now when I have these selected, you're going to see that both muscles are contracting now. Cool. Right, the next thing I'll get into is collisions. So up until now, we haven't been running any collisions. So what I'm going to do is I'm going to disable the the bicep for now. And so one of the nodes you get when you make the tissue is this Z tissue node, and this has some general properties about the tissue, one of which is enable, so you can disable a tissue at any time. So turn that off and hide it. And I'm just going to delete this sliding attachment as well, which I think was Z attachment 5. If you turn it, a good tip is if you turn envelope to 0, the color of the fiber changes so you can see which one you're dealing with. So delete that. Cool. So if I play this now, I think you'll see some intersections. I'll delete the fiber as well, just so it's obvious. Clear the cache. Go back to this. So you can see here that the tissue is going straight through the bone object. So what I'm going to do is you have to switch on collisions globally first. So by default, it comes in as off. So I'll just select the Z solver and then turn collision detection on. And then now clear that cache again. What I'm going to do is add an extra sub-step at this point. So it's quite a quick animation. And our collision model is a point in volume test. So if you have a quick motion and two of the bodies become more than halfway through each other, so for instance, like this, and it's going to be testing all of these points, right, to see if they're inside this object. And then, but if this body here becomes more than halfway through, it's going to not know which side to project the point back to. So in this case, it would go back to there. But this, because it's further than halfway through, it's going to go over there, which is going to cause problems. So we need an extra sub-step to make sure the collisions resolve. Now I'll clear the cache. And now hopefully, you can see all those penetrations are gone. The other thing that you'll notice as well is that if I go to a frame, if I go to Y-frame, you'll see now that we have these green collision proxy pairs, these proxy points. And this tells you when Ziva's determined that there was a point in volume intersection and that it's trying to push the objects apart. So that's what's happening with that. And so that's how you can tell when the collisions are working. And sometimes this is a really good debugging thing as well. So if your bodies do pass more than halfway through each other, you'll see the collision proxy pair will project to the wrong side and you'll be able to debug it, hopefully. Cool. So another thing that you'll notice when you make your tissue is that you get this Z material node, and this controls a couple of things. The two things it mainly controls are, or three things really, is the stiffness of the object, and this is defined by Young's modulus. And the reason we've called it Young's modulus and not stiffness is because Young's modulus is the engineering term for stiffness in the finite element method. So the cool thing is with this is that you can go onto Wikipedia or other resources and look up the Young's modulus for real world materials and plug those into Ziva, and our solver is going to replicate what those real world, is going to try and replicate what those real world materials do. So you can look up the Young's modulus for wood or diamond or gelatin or muscle, that sort of thing. So we've made it default to what a muscle is. And some other things we have here are these three attributes are to do with volume preservation or conservation, and then we have a density attribute. So if you want your muscle to bulge more, what I would do is Poisson's ratio and volume conservation are kind of two different systems for preserving volume. So I think it's good practice to use one or the other. So volume conservation is a better I think it does a better job of preserving volume. So usually if it's the bicep, for instance, and you really care about the bulge on the bicep, I'll just turn it back on. You could change this Z material to turn the Poisson ratio off and turn conservation to 10 times 10 to the 6, for instance. And volume conservation is going to be slightly slower, and but it's going to do a pretty good job of preserving the exact volume. You're seeing, hope that's all connected still. Yeah, so you get a really nice bulge happening in there now. So materials, the cool thing about materials is they're paintable. I'm just going to switch to another scene now to show a cool thing that you can do with materials. So in this scene, I have a really good application for materials or material layering is if you have a character with kind of armored plates or varying materials across the surface. So with this thing, you could think of this as the hide of a rhino or something like that, where these raised areas, we want them to preserve their shape, and we want the areas between the objects to deform, basically. So what I'll do is convert this to a tissue. With it selected, I'll add tissue, and then what I'm going to do is attach it to these bone objects. Oops. So if I play this back now, you're just going to see it. It's all going to kind of deform uniformly. That's fine. So the next thing we're going to do is I'm going to create a material layer. So with the object selected, we already have our default Z material, and then we can also add another one on top. So with it selected, under the Ziva menu, I can add tissue property material layer. You can see we've got this second material now. So these kind of function like layers in Photoshop, where the layer on top takes precedence. So I'm going to make the top layer 1,000 times more rigid than the bottom layer. So right now, if I play it back, it's going to the whole surface of the object is going to appear very stiff, which is what you would expect. And so now what I want to do is paint off the areas that aren't the raised plates. So again, I'll isolate the object so it's easier to see what's going on, and then I'll right click on the object, come down to paint, Z material 2 weights. Then I'll make sure I'm painting black. Oops. And I'm just going to paint these areas here. I won't do it too accurately because I know everybody's time is really valuable. So I'll do that. And then on this side. As well. Okay. Cool. So now when I play this back, you're going to see those areas try and preserve their shape a bit more. But you'll notice now that there's still not enough fidelity in the tet mesh to support the kind of deformation we want. So the great thing about our tet mesh is that we can adjust the resolution of it on the fly. So I could make the tets, for instance, if I select the object, we have this ZTet node, and this basically looks after everything to do with the tet mesh. So the first attribute here is tet size. So I can make this, say, 5. And it's going to non-destruct. The cool thing is that this is non-destructive, right? So I can change the tet size, which is the simulation component of the whole tissue. And I can change this non-destructively. So I haven't had to rebuild attachments. I haven't had to remesh anything. I can change the tet size whenever I want. And I might make this 4 now. And if I play this back, I'll just clear that cache if there was one. And so now you're starting to see that the areas between the plates are deforming a bit more, but they're still not really, it's not really doing the right thing. And there's probably still not enough resolution in the TEP mesh. There's not enough what we call degrees of freedom in the TEP mesh to support the sort of deformation that we want. So another cool feature is that you can paint the resolution of the TEP mesh as well. So if I right click on the mesh, come down to ZTEP1 weights, and I'll make sure I'm painting white. I'll just switch out of isolate mode for a second. So hopefully you better see. It's a bit hard to see, but the resolution of the TEP mesh is changing as I paint this. Let's go in here. Again, I won't get too accurate with it. But okay. So you can see that now when I change this, that the tets are smaller in the areas around the plates now. And what's happening is that map is multiplying against the surface refinement attribute. So you can think of this as subdivisions in mesh smooth. So the higher the value, the more subdivision. So if I change this to 2 now, you're going to see that we've got a whole lot of degrees of freedom in there. And if I play this back, hopefully we'll see some really nice deformation between the plates. So you can see that they're preserving their shape, and it's all kind of bending in the weaker areas. And I think we have a production example of that somewhere. So I'm not sure what the latency is going to be like for you guys, but this is an armored rhino with those plates, which is exactly how we solve that problem really quickly and really efficiently. So that's a fun thing you can do with Ziva. Okay. Right, so that I'm pretty sure is it for tissues for now. There might be one other thing that I want to show, which is called inertial damping, which I think is really important to show. What I'll do is select these objects. I'm just going to put a cluster on top of this. Form cluster. And I'm just going to make these bones move really sharply over maybe 3 frames. And delete some stuff here. Turn this off. And I'm also going to make the TEP mesh slightly smaller. Okay. And I'll turn collisions off as well for this. So you can see that when the character moved really quickly there, you got this kind of violent pull on the muscles. So this can happen a lot, right, with your shot work. You've got a character that you've set up for a walk cycle, for instance, and you want it to be working for a run or a climb or something, even something non-physical. Like sometimes you have your digi-doubles being thrown through the air and animations just pushing them at velocities that's not really possible. But we have this tool to help with that, and it's called inertial damping. So the cool thing about inertial damping is that it will negate all the world space motion out of your tissue solve. So it's not a normal damping that you might be used to, where it's going to, a normal damping is going to make your tissue look like it's moving through molasses or underwater or something. This is going to it's just going to pull out the world space motion. So all the collisions, all the gravity and stuff is still going to happen at the normal frequency. So if I just set this to 1 now, you'll see that when the character moves quickly, now you don't get that violent pull on that violent ballistic motion on the muscle. And so because it takes a float value, you can just say, I want, maybe I only want 50% of the world space motion. And if I play this back now, so it's still kept a bit of it, but for the most part, it's, it's pulled out 50% exactly. So you might have different configurations on your character. It might be effectively exactly the same character, but you have different inertial damping values for different animation context, if you like. So I think it's worth showing that because it's a really powerful shot tool. Okay, I think that is it now for tissues.